Okay, Assalamualaikum warahmatullahi wabarakatuh and a very good afternoon. So in this video, I'm going to explain on how the torque is induced in the DC motor. Okay. So let's see the construction. First, we need to see the construction of the DC motor first. Okay. In general, okay, for the permanent magnet DC motor, so this is the permanent magnet. So where we have the north poles and the south poles, and the direction of the magnetic field is from the north pole to the south pole. Okay, so in this explanation we are consider only a single loop, rotating loop. Okay, for a single coil only. Okay, so notice that the loop of the rotor wire lies in the slot curve in the ferromagnetic core. Okay, so you can see that the curve, so the magnetic field, the magnet is curved. Okay, and the rotor will be, if the rotor is rotate, it will become it's like a cylinder. Okay, so then the shape is like it's a curve. Okay, so the iron rotor together with the curved shape of the pole faces provide a constant width air gap between the rotor and the stator. Okay, remember from the previous chapter that the reluctance of the air is much higher than the reluctance of the iron in the machine. So to minimize the reluctance of the flux path through the machine, so the magnetic flux must take the shortest possible path through the air between the pole face and the rotor surface. Okay, so this is the stator. Okay, and this is the rotor. So the magnetic flux is not directly straightforward. It's not directly straightforward from here to here or here to here. Okay, so since the reluctance is higher in the air, so the magnetic field will take a shortest distance. So the shortest distance will always be the perpendicular to the rotor surface. Okay, so it will act perpendicular. You can see here at any direction in the curved surface. Okay, so this is important because later on we want to find the directions and the force direction and also the torque. Okay, so where the force is the formula of the force is ILB, and also the torque is RF sin theta. Okay, so the theta here is the angle between the R and F. Okay, so since the direction is always perpendicular, so the direction the angle will always be 90 degree. So please remember this. Okay, let's start with the DC motor. Okay, so now we add a power supply. We using a DC supply, which is the battery at here. So we connect with the resistor and the switch, and also the commutator. So we connect it to the motor. Okay, where the motor have the positive. We can connect anywhere. Okay, either the right to left or left to right. It's okay. So it will change the direction. So at this case, we supply a positive value, a positive side over here, and this is the negative side. Okay, so where the current will flow in this direction. Okay, will flow this direction, in this direction, and this direction. Okay, so the current direction is important to know where the force will be act. Okay, so over here we can see, if we draw like this, draw here for a single loop. Okay, so here we can see that the current is, the current is entering. Okay, Okay, we see from here, from the front face. Okay, and this point will be coming out. Okay, so the magnetic field will be in this direction. Okay, so now we have two parameters. Okay, so we have B, so which is the magnetic field, and also we have the current direction. Okay, so yeah, by using the Fleming left hand rule, okay, Fleming left hand rule, where okay, I just draw the hand. Okay, this is the thumb, and this is the middle. This is the index finger, and this is the middle finger. Okay, this is the other two. Okay, so where this is the direction of the force, and this is the direction of the magnetic field, and this is the direction of current. Okay, so by using the left hand rule, what do you think the direction of the force? Okay, so left and then inside, so the force will be downward. Okay, force will be downward. Okay, so how about this? Over here, so force will be so magnetic field to the left and current outside out of the page, and the force will be upward. Okay, so the motor will rotate. Okay, will rotate counter clockwise. Okay, so how to calculate? Okay, so how the motor, what happen when the motor is rotate? Okay, so there are 4 segments here. 4 segments. Okay, what is the total? Total torque. So there is 4 segments. Okay, so AB, so AB, BC, CD, and DA. Okay, so we have 4 segments. Okay, let's see at the segment AB first. Okay, the segment AB, so we can, when we look at the front, the direction is like this. Okay, so magnetic field is to the left, and the force will be upward. Okay, okay, so yeah, this is the formula for the force. Okay, so ILB, and then the formula for the torque. Okay, the formula for the torque is RF sine theta. So as I mentioned before, the theta is always 90 degree. Okay, so then this is the torque formula for the segment AB. So when the motion will be counterclockwise. So then the segment A as BC. So segment BC. So since the conductor here, so the conductor is parallel to the B. Okay, so this is direction of current, and this is direction of B. This is direction of current. Okay, and also the length. Okay, so since parallel, so the value will be 0. Okay, the value of force is 0, and the value of the torque also will be 0. So now the segment CD. Okay, the segment CD, as I mentioned before, the magnetic field is inward. Okay, and the magnetic the current direction is inward. The magnetic field is to the right, and the force will be downward. Okay, so we just put the formula. Okay, just enter everything, ILB and torque RF sine theta. So since 90 degree, so it will become RILB. Okay, so the motor will be rotate counterclockwise. Okay, and also the segment DA is equal to the segment BC, where the current and the length and also the magnetic field is in parallel. So the value will be 0. The value of the force and the torque will be 0. So we have a 4 segment. Okay, so how to total everything? Okay, so the resulting total induced torque on the loop is given by, we add everything. Okay, we just add everything, we name it as a torque induced. Okay, the torque induced equal to the torque AB, torque BC, torque CD, and torque DA. Okay, so we add together, and we have two things over here. So the resulting torque is 2R ILB. So under the pole faces. Okay, because if you can see, we draw again. Okay, so this is the faces. Okay, this is a face. Okay, this is face, and somewhere here, okay, somewhere here, the torque will be 0. Okay, this also, the torque will become 0 because there's no magnetic field somewhere here. Okay, so what happens? So the motor will move with force, and when they reach at this point, okay, at this location, okay, so for example here, the coil, and then they're moving up to here, so the coil will be slow. Okay, become slow, and then actually, if we calculate discrete, so since here they have a value of force, so there's force, and over here the force is equal to 0. Okay, so if we calculate discretely, so we found out at this point the motor will stop actually, but due to the inertia, so the motor already rotates, so due to the inertia, so the rotor will move. Okay, still moving. They should stop, but due to the inertia, they still move slowly until they reach the magnetic field. They receive another magnetic field, and they will become move faster again. Okay, so so this is the total. Okay, so this we can't see actually the real picture. So we want to try to simplify. We cannot see anything over here. We just see the 2, and then the radius, the R, the I, the L, and also the B. This we cannot see anything here. Okay, we try to not manipulate, but we try to simplify everything to the more meaningful equation. Okay, so then by using the fact that the area of the pole, okay, so when we calculate the area for the rotor, so to find the area of the rotor, okay, so this is R, okay, so we need to calculate, so this area of rotor is equal to 2 pi R L. So okay, so the whole surface for the it's like we call it a rotor or the cylinder over here. The formula for the cylinder, surface of the cylinder. So this is the formula. Okay, so since you can see that the pole is like a semicircle. Okay, so they only take the half of the rotor pole or the cylinder. Okay. Okay, so we just, even though they have 2 poles, so in the calculation we just take the one side only. Okay, so 2 pole, but we calculate by using a 1 pole only. Okay, so we have the area, and then we know that the flux is equal to AB. Okay, so in this case, the A is the area of the pole. Okay, area of the pole. So then we try to include these things inside. Okay, so we know that the 2 pi the pi RL is the area. Okay, so area is pi IL, and then for sure, when we want to replace, we can put like this, A over pi. Okay, so A over pi become RL. Okay, this is A pi, A pole. Okay, So we just to replace the R and L. Okay, so then we have A, we can replace A, and then we have the B. Okay, and then once we have that, so we have A. Okay, and then we put like this, A pi, and then AP B 2, right? So this AB, and there also one more I. So this AB is equal to the flux. Okay, so therefore we can replace as 2 over pi flux and I. Okay, so this is the resulting induced torque. Okay, the resulting induced torque for the DC motor for the single rotating loop. Okay, so we know already the formula and how is induced. So in general, the torque in any real machine will depend on the same 3 factor. Okay, in any DC motor, in any DC or any real machine. So from here we can see that it will depend on the 3 factor. Okay, the first factor actually is the flux in the machine. Okay, you can see here the flux. Okay, so we just look at the this formula. Okay, this is the flux. Okay, this is the factor. So the torque will be increased when you increase the number of the value of the magnetic flux. So when the magnetic flux increase, the torque will be increased, and also the current. Okay, the current of the machine. Okay, so when you increase the current, okay, when you increase the current, so the induced torque also will be increased. And the other thing is the constant representing the construction of the machine. So this is the constant. Okay, some of the books they call it as the replace as the K. So it is a constant. So number of coil, and then the number of pole. Okay, maybe the size and everything. Okay, so yeah, in general, so this is the factor. Okay, so how about the how about 4 poles and 10 coils. Okay, 10 rotating coil. How about this? Okay, so I want all of you to find out. Okay, and share the video or the comments. Okay, at the comment section. Okay, thank you.